And now in this lecture we'll answer two questions. In the first question, we find out the size of this angle AMQ is equals to x. We have to find out the value of x, the value of angle x. And in the second question, we find out the area of this circle that is inscribed by trapezoid ABCD. So we start with the first question. In the drawing, we have a semicircle. Point O is the center of this semicircle. AB is the diameter of this semicircle. In addition, we know that OS equals to SB. Inside this semicircle, we have square PQSO. Again, our task is to find out the size of this angle AMQ is equals to x. We have to find out the value of angle x. So first of all, we know that all the angles inside the square are right angles. So all those four angles are right angles. This is a right angle. This is also a right angle. And this is also a right angle. AB is the diameter of this semicircle. So AB as a diameter is absolutely a straight line. So if you focus on the upper side of the straight line AB at point S, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of the straight line AB at point S? We have this angle, that is a right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. We know that all the sides of any square are equal to each other. So in square PQSO, side OS equals to side SQ. So OS equals to SQ. You can write here that OS equals to SQ. Or SQ equals to OS. And it is given us the question that OS equals to SB. So from this equation, SQ equals to OS equals to SB, we will derive that SQ equals to SB. SQ equals to SB. So SQ equals to SB. Again, SQ equals to SB. In the next step, we will join points B and Q together by a straight line. And we'll extend the straight line BQ until it touches the circle. And we will define the touching point of the extended straight line BQ with this circle. This point is point N. By doing this construction, we created the right small triangle BSQ. this is the right small triangle BSQ. We have the rule that in front of equal sides in the triangle there are equal angles. Again, in front of equal sides in the triangle there are equal angles. So in front of those two equal sides in the right small triangle QSB, we have those two angles that must be also equal to each other and their sizes. So if we define the size of this angle as y, then the size of this angle must be also equal to y, because they are equal to each other according to the rule that I mentioned. We also know that the sum of the angles in any triangle is equal to 180 degrees. So the sum of the angles in the right triangle QSB must be equal to 180 degrees. So which angles we have in the right triangle QSB? We have this angle, this is y plus 90 degrees. In total it must be equal to 180 degrees. Y plus y is 2y, so 2y plus this angle that is 90 degrees. In total it must be equal to 180 degrees. So 2y plus 90 degrees plus 280 degrees. Here we subtract 90 degrees from this equation, and we get that 2y equals to 180 degrees minus 90 degrees is 90 degrees. So 2y equals to 90 degrees. Here we divide this equation by 2, and you get that the missing angle y equals to 90 degrees over 2 is 45 degrees. So this is angle y is equal to 45 degrees in its size. And this is also angle y is equal to 45 degrees in its size. We actually joined point B and Q by a straight line, and then we extended the straight line BQ by a straight line. We extended the straight line BQ by a straight line. In this way, we got line segment BN. When we extend a straight line by a straight line, the result is a straight line. So, therefore, BN is a straight line. So, if we focus on the left side of the straight line BN at point Q, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have in the left side of the straight line BN at point Q? We have this angle is equal to 45 degrees plus this angle, that is the right angle, plus this missing angle, which is actually angle NQP. In total, the sum of those three angles must be equal to 180 degrees according to rule 3. Repeat again. The sum of the angles of the left side of the straight line BN at point Q must be equal to 180 degrees according to rule 3. That is to say, 45 degrees plus 90 degrees plus the third missing angle, that is angle NQP. In total, they must be equal to 180 degrees according to rule 3. 45 degrees plus 90 degrees, it is 135 degrees. 135 degrees plus the missing angle NQP. In total, it must be equal to 180 degrees according to rule 3. Here we subtract 135 degrees from this equation, and we get the missing angle NQP equals to 180 degrees plus 135 degrees is 45 degrees. So the missing angle NQP equals to 45 degrees in its size. This is the missing angle NQP is equals to 45 degrees in its size. In the next step, we'll join points M and N together by a straight line. And we will join points N and N together by a straight line. By joining points N and A, we create triangle A and B. This is triangle A and B. Triangle A and B subtend on AB. AB is the diameter of this semicircle. And we know that according to rule 7, any triangle that subtend on the diameter of the semicircle or circle must be equal to 90 degrees in its size. So I repeat quickly rule 7. According to rule 7, if a peripheral angle subtend on the diameter of the circle, then it is equal to 90 degrees in its size. So in the drawing, we have a circle. This is peripheral angle ACB that subtend on AB, that is the diameter of this circle, and therefore peripheral angle ACB, according to this rule, rule 7, must be equal to 90 degrees in its size. So we can actually implement rule 7 in our drawing. In our drawing, we have peripheral angle A and B that subtend on AB, that is the diameter of this semicircle, and therefore, according to rule 7, peripheral angle A and B must be equal to 90 degrees in its size. So, in the big right angle A and B, this angle equals to 45 degrees, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 45 degrees in its size, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. This is angle MAN. This is angle NMA, or this is peripheral angle NMA. Peripheral angle NMA. Peripheral angle NMA. This angle subtend on chord NA. Likewise, this is peripheral angle ABN, peripheral angle ABN also subtend on the same chord called AN. And therefore, according to rule 16, those two peripheral angles that subtend on the same chord called AN must be equal to each other. So repeat quickly rule 16. According to rule 16, peripheral angles that subtend on the same chord are equal to each other. In the drawing of a circle, this is peripheral angle AOB, that subtend on chord AB. Likewise, we have peripheral angle ACB, that also subtend on the same chord called AB. And because of the fact that those two peripheral angles subtend on the same chord called AB, they must be equal to each other in their sizes. That is to say, this is peripheral AUB that must be equal to peripheral ACB because they are both subset on the same chord called AB, or alpha equals to beta. So we can implement rule 16 in our drawing. When put in our drawing, we have those two peripheral angles subset on the same chord called AN. And therefore, they must be equal to each other on their sides. But this peripheral angle ABN equals to 45 degrees, and therefore this peripheral angle AMN that also subset on the same chord called AN must also equal to 45 degrees inside according to rule 16. We focus on the big right triangle A and B. On the big right triangle A and B, in front of those two equal angles, we have those two sides that must be also equal to each other and their lengths, according to the rule that in front of equal angles in the triangle, there are equal sides. So that is to say, side AN in the right triangle ANB equals to side MB. And therefore, triangle A and B is also an isosceles triangle. Okay, again, triangle A and B is an isosceles triangle because side AN equals to side NB. So I write it down. The big right triangle, triangle A and B, is also an isosceles triangle because those two sides are equal to each other. So here we can implement rule 24. Repeat quickly on rule 24. According to rule 24, the perpendicular to the base of an isosceles triangle bisect the base. So in the drawing, we have the isosceles triangle, triangle ABC. Triangle ABC is an isosceles triangle because side AB equals to side AC. The base of the isosceles triangle, triangle ABC is BC. So from point A we do perpendicular to the base BC. Again, from point A we do perpendicular to the base BC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. And according to this rule 24, the perpendicular from point A to the base BC bisect the base BC. Again, the perpendicular from point A to the base BC bisect the base BC. That is to say, the perpendicular OA divides the base BC into two halves. Each half must be equal to BC over 2. And the first half BO must be equal to the second half OC, and each half equals to BC over 2. So you can actually implement rule 24 in our drawing. One put in our drawing, we have the isosceles triangle, triangle A and B. Again, triangle A and B is an isosceles triangle because side A equals to side NB. And according to rule 24, the perpendicular from point N to the base AB bisect the base AB. Again, the perpendicular from point N to the base AB bisect the base AB. AB is not only the base of the right triangle ABC, and of the right and associated triangle ABC, but AB is also the diameter of the circle, of the semicircle. Therefore, according to rule 24, the perpendicular from point N to the base AB bisect the base AB, but the base AB is also the diameter of the semicircle. So if the radius of this semicircle equals to R, then the diameter must be equal to 2R. So AB equals to 2R. The diameter AB equals to 2R. And according to rule 24, the perpendicular from point A to the base AB bisect the base AB. That is to say, it divides the base AB into two halves. Each half, of course, equals to AB over 2. AB over 2 is 2R over 2 because AB equals to 2R. 2R over 2 is R. So each half equals to R, that is the radius of the circle, the radius of the semicircle. So the first half equals to R, the second half also equals to R. The question is where the perpendicular from point N will touch side AB. The perpendicular from point N must touch the base AB at the midpoint of the base AB because it bisects the base AB, therefore it must touch the base AB at the midpoint of AB. The midpoint of AB is the midpoint of the diameter. The midpoint of AB is the midpoint of the diameter because the diameter is AB. And we know that the midpoint of any diameter, it is the center of the circle or semicircle. Again, the midpoint of any diameter is at the center of the circle or semicircle. Therefore, the midpoint of the diameter AB must be at point O, that is the center of the semicircle. Again, point O is the center of the semicircle. So, the perpendicular from point N to the base AB will touch the base AB at the midpoint of AB, that is the center of the semicircle, because AB is also the diameter of the semicircle. Therefore, the perpendicular from point N will touch the diameter AB at point O. So, we know that the opposite sides of a square are parallel to each other. So in square PQSO, those two, we have in square PQSO, side PQ is parallel to the opposite side OS. Those two angles are defined as corresponding angles, and we know that corresponding angles that are located between parallel lines are equal to each other. So, but before that, from point N we do perpendicular to AB. Again, according to our construction, from point N we do perpendicular to AB. Therefore, according to our construction, this angle equals to 90 degrees, and this angle also equals to 90 degrees. Okay, because NO is the perpendicular to AB. And we have the rule that corresponding angles, those two corresponding angles that are located between the parallel lines PQ and OS must be equal to each other. But this angle equals to 90 degrees, and therefore this angle must be also equal to 90 degrees in its size. According to the rule that corresponding angles that are located between those two parallel lines must be equal to each other. In the next step, I will prove that quadrilateral NMQP is a cyclic quadrilateral. That is to say, quadrilateral NMQP can be blocked or can be inscribed by a circle. Again, we prove that quadrilateral NMQP, this is quadrilateral NMQP, that it can be inscribed by a circle. It can be blocked by a circle. Okay, so first of all, what is the definition of a quadrilateral that is inscribed by a circle? Or what is the definition of a quadrilateral that is blocked by a circle? This is quadrilateral ABCD. The red quadrilateral is quadrilateral ABCD. Quadrilateral ABCD is blocked by this circle. Why? Because all of its four vertices touches the circle. Point A, point B, point C, and point D, they all touch the circle, and therefore quadrilateral ABCD is blocked by this circle. So a quadrilateral is blocked by a circle only and only if all of its four vertices touch the circle. So we have to prove that quadrilateral NMQP is inscribed, can be inscribed by a circle or can be blocked by a circle. So first of all, we have the rule that states that all triangles are cyclic. Again, all triangles are cyclic. That is to say, all the triangles in the world can be blocked by a circle. So I copied this triangle NQP in a new page. This is triangle NQP. In triangle NQP, this angle equals to 45 degrees. So I copied this triangle NQP to a new page, and we block this triangle NQP. This is triangle NQP that can be blocked by a circle because of the fact that all the triangles in the world can be blocked by a circle. So we blocked this triangle NQP by a circle. Okay, in triangle NQP, this is angle NQP that equals to 45 degrees in its size, and angle NQP subtend on chord NP. Again, angle NQP subtend on chord NP. So we have three vertices, Q, P, and N. This is a copy from the original drawing that are inscribed and that touches the circle. The three vertices Q, P, and N touches the circle. And in the drawing itself, in the original drawing, we have those two angles that are both equal to 45 degrees in their sizes, and they subtend on the base NP. Again, both those two angles, that each of them is equal to 45 degrees, subtend on the base NP. And therefore, those two angles fit to a circle. That is to say, they can be inscribed by a circle. They can be inscribed by a circle according to the rule that if the two peripheral angles subtend on the same chord, then they are equal to each other. Again, according to rule 16, if two peripheral angles subtend on the same chord, they are equal to each other. So those two angles, they are both subtend on NP, therefore can inscribe them by a circle, and then we get that those two angles will become peripheral angles. They are both subtend on chord NP, and therefore they are equal to each other. Each of them is equal to 45 degrees. That is to say, we can block these two angles by a circle, because they subtend on the same base NP. We have those two angles. This is angle NQP that subtend on chord PN, and this is angle PMN that is also subtend on the same chord NP. And it is also equal to 45 degrees in their sizes. And it is exactly according to rule 16. Those two peripheral angles, they are both subtend on chord PN, and therefore they are equal to each other. Each of them equals to 45 degrees, and therefore they are equal to each other. Exactly according to rule 16. Actually, what happens if we will have another angle that subtend on chord PN? We have another angle that subtend on chord PN, but it is located outside the circle. This is angle PLN. It's located outside this circle, and it subtend on chord PN. Actually, I measured this angle by scale, and this angle equals to 39 degrees in its size. That is to say, we can say in general that all the angles that are located outside this circle and they subtend on the same chord PN, they will be less than 45 degrees. All the angles. You can can draw another angle that is located here, and we create an angle that is also subtend on chord Pn. This angle will be less than 45 degrees. Likewise, if we draw another angle that is located inside this circle, like this angle that is PON, this is angle PON, that is also subtend on the same chord Pn. I measured this angle by scale, and this angle equals to 85 degrees in its size. That is to say, you can say that all the angles that are located inside this circle that and subtend on chord Pn will be bigger than 45 degrees. So in general, we can say that all the angles that are located outside this circle and the subtend on Pn will be less than 45 degrees, while all the angles that are located inside this circle and subtend on the same chord Pn will be bigger than 45 degrees. Like this angle, it is located inside this circle and it is equals to 85 degrees in its size. Therefore, we can say in general that only the angles that are inside this circle, that touches the circle, the vertex of the angle touches the circle, and they subtend on chord Pn, only those angles will be equal to 45 degrees in their sizes. Okay? Only the angles that subtend on chord Pn and touches the circle will be equal to 45 degrees in their sizes. That is to say, only the peripheral angles that are on this circle will be equal to 45 degrees in their sizes. All the other angles, for example, all the angles that are located outside this circle, or the angles that are located inside this circle, will not be equal to 45 degrees in their sizes. Either they will be greater than 45 degrees, or they will be greater than 45 degrees, or less than 45 degrees. So all the angles that can be equal to 45 degrees in their sizes, and at the same time there will be subtended on chord Pn, they are located inside on the circle itself. That is to say, they are peripheral angles. Okay, so here this is peripheral angle PQN that subtend on chord Pn, and it is equals to 45 degrees in its size. I copied this peripheral angle from the original drawing, and we blocked this triangle by a circle because all the triangles in the world can be blocked by a circle. So we know that according to the rule that I mentioned, only the angles that are located inside on the circle itself, that is to say peripheral angles, they are both will be equal to 45 degrees in their sizes. So the angles that subtend on Pn and they are on this circle will be equal to 45 degrees in their sizes. All the other angles will not be equal to 45 degrees in its size, in their sizes. So if we rotate this angle, this peripheral angle that is 45 degrees in its size, if we rotate it around this circle without changing the size of this angle, if we rotate this angle around this circle, we create infinite angles that each of them is equal to 45 degrees in its size. One of those angles will be angle PMN, that equals to 45 degrees in its size, and it's subtend on chord Pn. And this is angle PMN, that equals to 45 degrees in its size, and it's subtend on chord Pn. So in this way, and in the next step, we'll join points M and Q together by straight line. So by doing all those operations, we created quadrilateral NMQP that is definitely inscribed by this circle. So in this way, we actually prove that quadrilateral MNQP can be inscribed by circle, because this is the circle that inscribes triangle and quadrilateral NMQP. Okay, so in conclusion, we can say that quadrilateral QMNP definitely can be inscribed by circle. So we can write down that this is quadrangle nm cubic, that is definitely can be inscribed by circle. So in the long if you found that quadrangle mn QP is a cyclic quadrilateral. That is to say, it can be inscribed by circle. It can be blocked by circle. It's a cyclic so we can block this quadrilateral NMQP by circle. So I can actually block this quadrilateral by circle. So we'll do it now. You can see that the red circle inscribed this quadrilateral NMQP. Why the red circle inscribes quadrilateral NMQP? Because of the fact that all of the four vertices of quadrilateral NMQP lie on the red circle. This is point M that lies on the circle, point M, point Q, and point P. They are both lie on the red circle, and therefore quadrilateral NMQP is inscribed by this red circle. So here we can implement the rule that says that the sum of the two opposite angles in a cyclic quadrilateral is equal to 180 degrees. Repeat again. According to the rule, the sum of the two opposite angles in a cyclic quadrilateral is equal to 180 degrees. So, in quadrilateral NMQP, those are the two opposite angles, and the sum of those two opposite angles must be equal to 180 degrees according to the rule that I read to you. So this is angle NPQ, that is the right angle, plus this angle, that is angle NMQ. In total, they must be equal to 180 degrees. So write it down. Angle NPQ plus the opposite angle NMQ. In total, they must be equal to 180 degrees according to the rule that I read to you. This is angle NPQ, that is the right angle, plus this angle NMQ. Angle NMQ in total equals to 45 degrees plus x. In total, they must be equal to 180 degrees. 90 degrees plus 45 degrees is 135 degrees. Plus the missing angle x, that is the angle that you're looking for in this question. In total, it must be equal to 180 degrees. Here we'll subtract 135 degrees from this equation. And we get that the missing angle x equals to 180 degrees minus 180 degrees minus 135 degrees equals to 45 degrees. So the missing angle that we are looking for, this is angle x. This is also defined as angle AMQ. Is equal to 45 degrees in its size. And this is the answer to the first question. Repeat again. This is the missing angle AMQ. This is equals to x, and it is equals to 45 degrees in its size. So we finish with the first question. In the next step, I will present to you the second question and resolve the second question of this lecture. In the second question, our text is to find out the area of this circle that is inscribed by trapezoid ABCD. So first of all, what is a trapezoid? A trapezoid is a quadrilateral with one pair of parallel sides. This is quadrilateral ABCD. In quadrilateral ABCD, side DC is parallel to the opposite side AB, and therefore quadrilateral ABCD is a trapezoid because it has one pair of parallel sides. If we define the two parallel sides are defined as the bases of the trapezoid. DC is the first base and AB is the second base. So if we define the length of the base DC as A and the length of the base AB as B, this is to say the length of the base AB is equal to B units according to our definition. Then the area of this trapezoid ABCD will be equal to the sum of its two parallel bases, that is to say A plus B times the height edge over 2. The height edge must create 90 degrees with the two parallel bases. So a trapezoid is a quadrilateral with one pair of parallel sides, and the area of a trapezoid equals to the sum of its two parallel bases times the height over 2. The height edge must create 90 degrees with the two parallel bases. So our task is to find out the area of this circle that is inscribed by trapezoid ABCD. In addition, we know that those two angles, they are both right angles. The area of this trapezoid ABCD is equal to 3 square units in its size, and the length of side AB is 3 units. Again, our task is to find out the area of this circle. So first of all, we define the center of this circle. This point is point O. In addition, we define the relevant points to this question with letters. We define the point of tendency of tangent DC. With this circle, this point is point E. We define the point of tendency of tangent DA. With this circle, this point is point F. We define the point of tendency of tangent AB with this circle. This point is point G. We define the radius of this circle as X. In the next step, we will join points O and G together by straight line. Point O is the center of the circle, point G is the point of the circle itself, therefore OG is the radius of this circle, is equals to X. So here we can implement rule 1, and keep clicking on rule 1. According to rule 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. In the drawing, we have a circle. This is tangent AB, that is tangent to the circle at point M. In addition, we have the radius OM, that is equals to R. The radius OM is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever your radius is drawn to the point of tendency, then tangent AM will be perpendicular to the radius MO. If AM is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to this rule, rule 1. So we can actually implement rule 1 in our drawing. Because in our domain, we have the radius OG that is equals to x. The radius OG is 1 to point G, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is 1 to the point of tendency, then tangent AB will be perpendicular to the radius GO. If AB is perpendicular to GO, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule 1. Likewise, we join points O and F together by a straight line. OF is of course the radius of this circle, is equal to x, and according to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. Likewise, we join points O and E together by a straight line. OE is of course the radius of this circle, is equals to x. And according to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. So in the upper quadrilateral OE, OF, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this 4 pieces angle, in total it must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees, and therefore this 4 pieces angle must be equal to 90 degrees in its size. So in quadrilateral DEOF we have 4 right angles, therefore we can, according to rule 5, any quadrilateral that has 4 right angles must be at least right angle if not a square. So we have to quadrilateral DEOF as right angle because it has 4 right angles. But you also know that the opposite sides of a rectangle are equal to each other. So rectangle DEOF, side EO equals to the opposite side DF. But EO is x, therefore the opposite side DF must be also equal to x units in its length. Likewise, in the lower quadrilateral FOGA, we have 1, 2, 3 right angles, and therefore this 4 pieces angle must be equal to 90 degrees in its size. So in quadrilateral EFOGA, we have 4 right angles, therefore we can relate to this quadrilateral FOGA as a rectangle. But we also know that the opposite sides of a rectangle, are equal to each other. So in rectangle FOGA, side OG must be equal to the opposite side FA. But OG is x, therefore the opposite side FA must be also equal to x units in its length. So actually we found out that the length of side DA of trapezoid ABCD equals to x plus x, that is 2x. So DA equals to 2x units in its length. We define the length of side DC as A, and according to what is given in the question, AB equals to 3 units in its length, CB is the missing side. We have already proved that in trapezoid ABCD, DA plus the opposite side CB equals to DC plus AB. It is true according to rule 2, so I will not repeat on the sub proof, and use it on this lecture. So we already proved that DA plus CB equals to DC plus AB according to rule 2. So in trapezoid ABCD, DA plus the opposite side CB is equal to DC plus the opposite side AB. So according to all two. And again, we already proved that in trapezoid ABCD, DA plus CB equals to DC plus AB. Actually, it is true in any trapezoid. DA equals to 2x plus CB. CB is the missing side, so where it is. And it is equals to DC. DC is A, according to our definition, plus AB. AB is equals to 4 units in length, according to what is given in the question. So in total, we found out that 2x plus CB equals to A plus 3. Here we subtract 2x from the equation, and we get that the missing side CB equals to A plus 3 minus 2x units in its length. So here, this is the missing side CB, that in total is equals to A plus 3 minus 2x units in its length. In the next step, we will do a construction, that is to say, from point C, we will go perpendicular on AB. Again, from point C, we will go perpendicular on AB. And we will define the touching point of the perpendicular from point C and AB. This point is point M. By doing this construction, we're going to do quadrilateral DCMA. This is quadrilateral DCMA. In quadrilateral DCMA, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this 4 pieces again. In total, they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore, this 4 pieces again must be equal to 90 degrees in its side. So in quadrilateral DCMA, we have 4 angles, and therefore, according to rule 5, we can relate to quadrilateral DCMA is a rectangle, because it has 4 angles. But you also know that the opposite sides of a rectangle are equal to each other. So in the big rectangle DCMA, side DC must be equal to the opposite side AM. But DC is A, therefore the opposite side AM must be also equal to A units in its length. Likewise, according to the same rule, in the same rectangle DCMA, side DA must be equal to the opposite side CM. But DA is 2x, therefore the opposite side CM must be also equal to 2x units in its length. What is the length of this missing line segment? Line segment MB. From the drawing it is very easy to see that MB equals to AB minus AM. Again, AB minus AM equals to MB. So write it down. MB equals to AB minus AM. So MB in total equals to AB is 3, according to what is given in the question, minus AM. We just write down found out that AM equals to A. So in total, MB, the missing side MB equals to 3 minus A units in its length. MB equals to 3 minus A units in its length. In the next step, I'll copy the big right triangle CMB in a new page, and we will implement on this big right triangle CMB the Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is the relation for Pythagoras theorem. The hypotenuse CB equals to A plus 3 minus 2x in its length. Side CM equals to 2x units. And side MB equals to 3 minus 3 units in its length. So actually, this is the right triangle CMB, then the comment from the original drawing. In this right triangle CMB, according to the Pythagoras theorem, CB squared, that is the square of the hypotenuse, equals to CM squared plus MB squared. The hypotenuse CB equals to A plus 3 minus 2x. Therefore CB squared equals to A plus 3 minus 2x squared. And it is equals to CM squared. CM is 2x, therefore CM squared is 2x squared. 2x squared is 4x squared plus MB squared. MB is 3 minus A, therefore MB squared is 3 minus A squared. So in total we found out that A plus 3 minus 2x squared equals to 3x squared plus 3 minus A squared. We'll open the brackets on both sides of this equation. We'll open the brackets according to the algebraic identity that states that A minus B squared equals to A squared plus B squared minus 2 times A times B. And therefore according to the algebraic identity that I mentioned, A plus 3 minus 2x squared equals to A plus 3 squared plus 2x squared, that is 4x squared, minus 2 times A plus 3 times 2x, and it is equals to 4x squared plus 3 minus A squared. 3 minus A squared equals to 3 squared, that is 9, plus A squared minus 2 times 3 times 8, that is minus 6A. We'll open the brackets of this expression, A plus 3 squared. A plus 3 squared equals to A squared plus 3 squared, that is 9, plus 2 times A times 3, that is 6A, plus 4x squared, minus 2 times 2x is minus 4x, so in total this expression equals to minus 4x times A plus 3. And it is equals to 4x squared plus 9 plus a squared minus 6a. So here we have a squared on both sides of this equation. So a squared gets cancelled. We have also 9 on both sides of this equation. So 9 also gets cancelled. And we have 4x squared on both sides of this equation. So 4x squared also gets cancelled. After we cancel all those expressions in this side of the equation, we're left only with 6a minus 4x times a plus 3. When on the other side of the equation, we're left only with minus 6a. So if we found out that 6a minus 4x times a plus 3 equals to minus 6a. So here we get 6a and 4x plus a plus 3 simultaneously to this equation, and we'll get that 6a times 6a plus 6a is 12a equals to 4x times a plus 3. Here we divide this equation by 4, and we get that 12a over 4 is 3a. So 3a equals to 4x over 4 is x, so in total this expression equals to x times a plus 3. So in total we found out that 3a equals to x times a plus 3. Here we will divide this equation by a plus 3, and finally we get that x equals to 3a over a plus 3. Okay, again, we should find out that x equals to 3a over a plus 3. X is the radius of the circle. In the next step, we find out the area of this trapezoid ABCD according to the formula that I presented to you at the beginning of the lecture. So the area of trapezoid ABCD will be equal to the sum of its two parallel bases, that is actually DC plus AB, times the height. The height is cm because it's greater than the width with the two parallel bases, times the height cm over 2. So in total, if you found out that the area of this trapezoid ABCD equals to the sum of its two parallel bases, that is actually DC plus AB, times the height cm over 2. DC equals to A plus AB. AB equals to 3 units in itself, according to what is given in the question, times CM. CM equals to 2x, and CM equals to 2x over 2. So in total, we should know that the area of this trapezoid ABCD equals to A plus 3 times 2x over 2. We have 2 in the numerator and 2 in the denominator, so 2 gets cancelled. So we cancel 2, if you found out that the area of trapezoid ABCD in total is equals to A plus 3 times x units, A plus 3 square units in its size. A plus 3 times x square units in its size. Okay, again, the area of trapezoid ABCD equals to A plus 3 times x square units in its size. But we already found out that x equals to 3a over a plus 3. And again, x equals to 3a over a plus 3, so we can substitute x here by 3a over a plus 3. We do it now, and we get that the area of trapezoid ABCD equals to a plus 3 times x, and x is 3a over a plus 3. But it is given as a question that the area of trapezoid ABCD equals to 3 square units in its size. So we substitute the area of trapezoid ABCD by 3, and again that 3 equals to a plus 3 times 3a over a plus 3. So we have a plus 3 in the numerator and a plus 3 in the denominator, so a plus 3 will get cancelled, and we're left only with 3 equals to 3a. 3 equals to 3a. Here we divide this equation by 3, and finally we get that a equals to 3 over 3 is 1, so a equals to 1 unit in its length. And then, according to this equation, x equals to 3a over a plus 3, and a equals to 1. So we substitute a in the equation by 1. And we get that x equals to 3a. A is 1, so 3a is 3 times 1, that is 3, over a plus 3. A is 1, so a plus 3 is 1 plus 3, that is 4. So in total we should find out that the area of the circle is equal to 3/4 units in its length. The area of the circle, the radius of the circle, x, is the radius of the circle, that equals to 3/4 units in its length. The radius of this circle, x, equals to 3/4 units in its length. Our task is to find out the area of the circle. So what is the area of the circle? Actually, we know that the area of any circle equals to pi times the radius of the circle squared. And repeat again, the area of any circle equals to pi times the radius of the circle squared. And therefore, the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle squared is x squared. So the area of our circle must be equal to pi x squared. So it is pi times x squared. X is 3, x is 3/4, x equals to 3/4, and therefore x squared is 3/4 squared. 3/4 squared is 3 squared, that is 9, over 4 squared, that is 16. So in total we should find out that the area of this circle, that is the area that we are looking for in this question, is equal to either 9 pi over 16 square units in its size, or in terms of numbers it is equal to 1.767 square units in its size. And again, if we find out that the area of this circle, it is equal to either 9 pi over 16 square units in its size, or in terms of numbers, the area of this circle equals to 1.767 square units in its size. So we finish with the second question. In the next step, I'll start with the lecture. We'll start with the first question, of course. In the first question, our task is to find out the size of this angle AMQ is equals to x. We have to find out the value of angle x. So in the drawing, we have a semicircle. Point O is the center of the semicircle. AB is the diameter of the semicircle. In addition, we know that OS equals to SB. Inside this semicircle, we have square PQSO. Again, our task is to find out the size of this angle AMQ. This is equals to x. We have to find out the value of angle x. So first of all, we know that all the angles inside the rectangle are inside the square are right angles. So those four angles are all right angles. And in addition, we know that all the sides of any square are equal to each other. That is to say, side OS equals to side SQ. OS equals to SQ. But it is given as a question that OS equals to SO. OS equals to SO. And from this equation, SQ equals to OS equals to SB, we will derive that SQ equals to SB. SQ equals to SB. SQ equals to SQ equals to SB. Again, SQ equals to SB. Those two sides are equal to each other. Okay, so in the next step, we join points B and Q together by a straight line. Then we extended the straight line BQ by a straight line until it touches the semicircle at this point. We define the touching point of the extended side as BQ. If this circle, this point is point N. Those two sides are equal to each other in triangle, the right triangle BQS. Those two sides are equal to each other. SQ equals to SB. And remember the rule that in front of equal sides in the triangle there are equal angles. So in front of those two equal sides we have those two angles that must be also equal to each other in their sizes. So if we define the size of this angle as y, then the size of this angle must be also equal to y because they are equal to each other. And we know that the sum of the angles in any triangle is equal to 180 degrees. So the sum of the angles in triangle SQB must be equal to 180 degrees. Which angles we have in the right triangle SQB? We have y plus y, that is 2y plus 90 degrees. In total must be equal to 180 degrees according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So in the right triangle SQB or QSB, the sum of the angles must be equal to 180 degrees. That is to say 2y plus 90 degrees equals to 180 degrees. If subtracted 90 degrees from this equation, if I found out that 2y equals to 180 degrees minus 90 degrees is 90 degrees. If we divided this equation by 2, if I found out that the missing angle y equals to 90 degrees over 2 is 45 degrees. So this is the missing angle y that is equals to 45 degrees in its size, and this is also the missing angle y that is also equals to 45 degrees in its size. We actually joined points B and Q together by a straight line, and then we extended the straight line BQ by a straight line. When we extend the straight line by a straight line, the result Bn must be also a straight line. So Bn is a straight line. So if you focus on the left side of the straight line, Bn is point Q. Here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles from one side of a straight line is equal to 180 degrees. So which angles we have at the left side of the straight line and B at point Q? We have this angle that is 45 degrees, plus this angle that is 90 degrees, plus this missing angle that is occurring again in QP, so that must be equal to 180 degrees according to rule 3. Then again, in the left side of the straight line Bn is point Q, the sum of the angles must be equal to 180 degrees according to rule 3. So which angles we have at the left side of the straight line Bn is point Q? We have 45 degrees plus 90 degrees plus the missing angle in QP, so that must be equal to 180 degrees according to rule 3. 45 degrees plus 90 degrees is 125 degrees, plus the missing angle in QP, total must be equal to 180 degrees. We have subtracted 135 degrees from this equation. and find out that the missing angle NQP equals to 180 degrees minus 135 degrees is 45 degrees. So this is the missing angle NQP. This equals to 45 degrees in its size. In the next step, we join points M and N together by a straight line, and we also join points N and A together by a straight line. By doing this construction, what we can do? Triangle A and B. Triangle A and B subtend on AB, this is the diameter of the semicircle, and according to rule 7, any triangle that subtend on the diameter of the circle or semicircle must be equal to 90 degrees in its size. Therefore, triangle A and B must be equal to 90 degrees in its size according to rule 7. Those two angles, that is to say angle AMN, subtend on chord AN. Likewise, this is angle ABN, that is also subtend on the same chord called AN. And because of the fact that those two angles subtend on the same chord called AN, they must be equal to each other in their sizes. But the size of this angle is 45 degrees, and therefore the size of this angle must be also equal to 45 degrees. According to rule 16, rule 16 says that if two angles subtend, if two or more angles subtend on the same chord, they are equal to each other in their sizes. Okay? So, we have here the right triangle BNA. In the right triangle BNA, this angle equals to 45 degrees. This angle equals to 90 degrees according to rule 7. And therefore, this third missing angle must be equal to 45 degrees in its size, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So, in the right triangle, the right big triangle A and B, in front of those two equal angles, we have those two sides that must be also equal to each other in their lengths, according to the rule that in front of equal angles in the triangle, there are equal sides. So, those two angles must be equal to each other. That is to say, AN equals to NB in the right triangle NB. And because of the fact that AN equals to NB in the right triangle NB, the right triangle NB is also an associated triangle, because those two sides are equal to each other. And again, in the right triangle NB, we have those two sides that are equal to each other, therefore the right triangle NB is also an associated triangle. So here we can implement. We know that the base of the associated triangle NB is AB. AB is also the diameter of this semicircle. So here we can implement rule 24. According to rule 24, the perpendicular to the base of an associated triangle bisect the base. So we can implement rule 24 in our drawing. Why? Because in our drawing we have the associated triangle A and B. And according to rule 24, the perpendicular to the base AB bisect the base AB. The base AB is also the diameter of the semicircle. So if the radius of the semicircle is r, then the diameter must be equal to 2r. So AB equals to 2r because it is the diameter of the semicircle. The perpendicular from point N bisects the diameter AB. That is to say, it divides this into two halves. Each half must be equal to AB over 2 or 2r over 2. Each half equals to AB over 2. AB over 2 is 2r over 2 because AB is the diameter, is equals to 2r. 2r over 2 is r, so the first half equals to r and the second half equals to r. But the question is where the perpendicular from point N to the base AB will touch AB. The perpendicular from point N bisects the base AB. Therefore, the perpendicular from point N will touch AB at the midpoint of AB. AB is the diameter of the semicircle. And we know that the midpoint of the diameter of the circle or semicircle, it is in the center of the semicircle or circle. Therefore, the midpoint of the diameter AB must be at point O, that is the center of the semicircle. So, the diameter NO bisects AB again, the perpendicular NO bisect the diameter AB, each half equals to R, and it touches the perpendicular NO, the perpendicular from point N, touches the diameter AB at point O, that is the center of the semicircle. So it is perpendicular from point N. That is to say, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. Note that the opposite sides of a square are parallel to each other. So in square PQSO, side OS is parallel to the opposite side PQ. And we have the rule that corresponding angles between parallel lines are equal to each other. So those two corresponding angles that are located between the parallel lines OS and PQ must be equal to each other. But this angle equals to 90 degrees, and therefore this angle must be also equal to 90 degrees in its size. In the next step, I prove that quadrilateral NMQP is a cyclic quadrilateral. So first of all, what is the meaning of the sentence that a quadrilateral is a cyclic quadrilateral? That is to say, it means that all the four vertices of the quadrilateral touch the circle. This is quadrilateral ABCD. The red quadrilateral ABCD is inscribed by this circle, why? Because all of its four vertices, A, B, C, and D, touch the circle. So a quadrilateral that is inscribed by a circle means that all the four vertices touch the circle at different points. You can see all the four vertices A, B, C, and D touch the circle. We have to prove that quadrilateral NMQP is a cyclic quadrilateral. That is to say, it can be inscribed by a circle. So first of all, I copied this triangle NQP in a new page. This is triangle NQP that I copied from the original drawing. We know that angle NQP equals to 45 degrees in its size. So this is triangle NQP that I copied from the original drawing. And we have the rule that all the triangles in the world can be inscribed by a circle. All the triangles are cyclic. Therefore, that is to say, we can block this triangle NQP by a circle. So I block this triangle NQP by a circle, and those two angles are both equal to 45 degrees in the sides, and they subtend on the base NP. Again, this is angle PMN that subtend on the base NP, and this is angle PQN that is also subtend on the same base PN. And therefore, those two angles actually can be inscribed by a circle. Those two angles are equal to each other in their sizes, and they subtend on the same base NP, and therefore they can be inscribed by a circle. According to the rule 16, that states that five angles that subtend only on the same chord are equal to each other. Okay? So here we have those are the two peripheral angles. This is peripheral angle NQP that subtend on chord NP. Likewise, this is peripheral angle PMN that is also subtend on the same chord called NP. For that reason, they are equal to each other on their sizes. And therefore, it means that we can inscribe those two angles by a circle. But what about angles that subtend on the same chord PN but are located outside this circle? For example, this is angle PLN that is definitely located outside this circle, in this point, and it subtends on the same chord PN. you can check it that all the angles that are located outside this circle and subtend on chord Pn will be less than 45 degrees. Like this angle PLN that is located outside this circle and it is equal to 39 degrees in its size. Likewise, all the angles that are located inside this circle, for example, this is angle PON that is located inside this circle and subtend on chord Pn, it is equal to 85 degrees in its size, that is bigger than 45 degrees. So all the angles that are located outside the circle and subtend on chord Pn are less than 45 degrees, while all the angles that are located inside this circle and subtend on the same chord Pn will be greater than 45 degrees. Therefore, only the angles that are located on the circle itself that subtend on chord Pn will be equal to 45 degrees in their sizes. Okay, only the angles that are located inside this circle and the subtend on chord Pn they will be equal to 45 degrees in their sizes. So we can actually rotate this angle NQP without changing the size of this angle. This is 45 degrees. We can rotate it along this circle. This way we create infinite angles that each of them equals to 45 degrees in its size, and it is subtend on the same chord Pn. Because chord Pn is the axis of the angle, it doesn't move. We just rotate the vertex along this circle. Therefore, all the angles that will be created are subtend on the same chord Pn, and all the angles will be equal to 45 degrees in their sizes because we will not change the size of this angle. So we create infinite angles that each of them is equal to 45 degrees in its size and it's subtend on chord Pn. One of the angles that will be created is angle PMN, that is equal to 45 degrees in its size and it's subtend on chord Pn. Exactly like in the original drawing, we have this is angle PQN, that is equal to 45 degrees in size, and this is angle PMN, that is equal to 45 degrees in size, and it's subtend on the same chord Pn. In the next step, we will join points P and N together by a side line. In this way, we create quadrilateral PNQP, PMQP. This is quadrilateral PMQP that is definitely inscribed by this circle. So in this way, we can prove that quadrilateral PQMN can be inscribed by a circle. Okay. So actually, draw this red circle that inscribes quadrilateral NMQP. Quadrilateral NMQP is inscribed by this red circle because of the fact that all of its 4 vertices lie on the circle, the red circle. Vertex N, vertex M, vertex Q, and vertex P, they all lie on the circle, and therefore quadrilateral NMQP is inscribed by this circle. And we have the rule that says that any quadrilateral that is inscribed by a circle, the sum of its 2 opposite angles is equal to 180 degrees. So quadrilateral NMQP is inscribed by this red circle, and therefore the sum of those 2 opposite angles in quadrilateral NMQP will be equal to 180 degrees according to the rule that I mentioned. So first of all, we prove that quadrilateral NMQP is a cyclic quadrilateral. That is to say, it can be inscribed by a circle, and the sum of the 2 opposite angles in a cyclic quadrilateral is equal to 180 degrees. That is to say, angle NPQ plus the opposite angle NMQ must be equal to 180 degrees. Angle NPQ is a right angle, and angle NMQ equals to 45 degrees plus x. Angle NPQ equals to 90 degrees, and angle NMQ equals to 45 degrees plus x. And in total, they must be equal to 180 degrees according to the rule they mentioned. 90 degrees plus 45 degrees is 135 degrees. So 135 degrees plus x equals to 180 degrees. Here we subtract 135 degrees from this equation. If I found out that the missing angle x, that is the angle that we are looking for this question, is equal to 100 degrees minus 135 degrees is 45 degrees. So angle AMQ is equal to x is equal to 45 degrees in its size. So we finish the first question. In the next step, I presented to you the second question, and we solve the second question of this lecture. In the second question, our task is to find out the area of this circle that is described by trapezoid ABCD. So, first of all, what is a trapezoid? A trapezoid is a quadrilateral with one pair of parallel sides. And again, a trapezoid is a quadrilateral with one pair of parallel sides. In the drawing, you have quadrilateral ABCD. In quadrilateral ABCD, side DC is parallel to the opposite side AB. Therefore, quadrilateral ABCD is a trapezoid because it has one pair of parallel sides. The two parallel sides DC and AB are defined as the bases of the trapezoid ABCD. So if we define the length of the base DC as A and the length of the base AB as B, then the area of this trapezoid ABCD will be equal to the sum of its two parallel bases, that is to say A plus B times the height H over 2. The height H must create 90 degrees with the two parallel bases. So in conclusion, if we found out that a trapezoid is quadrilateral with one pair of parallel sides, and the area of any trapezoid equals to the sum of its two parallel bases. In this case, it is A plus B times the height H over 2. The height H must create 90 degrees with the two parallel bases. So in addition, we have in the drawing those two angles that are both equal to 90 degrees. And we know that the area of this trapezoid ABCD equals to 3 square units in its size, and side AB equals to 3 units in its length. And this circle is inscribed by trapezoid ABCD. Our task is to find out the area of this circle. So first of all, we defined the relevant points to this question with letters. We defined the center of this circle, this point is point O. We defined the point of tendency of tangent DC with this circle, this point is point E. Likewise, we define the point of tendency of tangent DA with this circle, this point is point F. And finally, we define the point of tendency of tangent AB with this circle, this point is point G. Also defined the radius of this circle as X. Okay? In the next step, we join points O and G together by a side line. Point O is the center of the circle, point G is the point of the circle itself, therefore OG is the radius of the circle, this is equal to X. The radius of OG is equal to X. The radius of OG is 1 to point G, that is the point of tendency of tangent AB with this circle. Whenever you have a radius that is 1 to the point of tendency, then tangent AB will be perpendicular to the radius GO. If AB is perpendicular to GO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we join points O and F together by a straight line. OF is of course the radius of this circle, that is equals to X. The radius OF is equals to X, and according to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. Likewise, we join points O and D together by a straight line. O is of course the radius of this circle, that is equals to X. And according to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. So in the upper quadrilateral DEOF, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the sides of this 4 pieces angle in total must be equal to 360 degrees. According to the rule, then the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this 4 pieces angle must be equal to 90 degrees in its size. So in quadrilateral DEOF we have 4 right angles. Therefore quadrilateral DEOF is a right angle. But we also know that the opposite sides of rectangle are equal to each other. So in the small rectangle DEOF, side EO must be equal to the opposite side DF. But EO is X, therefore the opposite side DF must be also equal to X units in its length. Likewise, in the lower quadrilateral FOGA, we have 1, 2, 3 rectangles, and therefore this 4 piece angle must be equal to 90 degrees in its size. Therefore quadrilateral FOGA is at least a rectangle if not a square. We relate to quadrilateral FOGA is a rectangle, but we also know that the opposite sides of a rectangle are equal to each other. So a rectangle FOGA, side OG must be equal to the opposite side FA. But OG is X, therefore the opposite side FA must be also equal to X units in its length. So in total, the length of side DA of trapezoid ABCD equals to X plus X, it is 2X. Again, d8 is definitely a straight line because it is one side of trapezoid ABCD. Likewise, we define the length of side DC as A. We know that AB equals to 3 units in its length, and CB is the only missing side. We have already proved that in any trapezoid, DA plus CB equals to DC plus AB. Again, according to rule 2, DA plus CB equals to DC plus AB. So I'll not repeat on the same proof again. So we'll use it in our lecture. We already proved that according to rule 2, DA plus CB equals to DC plus AB. DA is 2x plus CB. CB is the missing side, so it is. And it is equals to DC. DC equals to A plus AB. AB equals to 3 units in its length according to what is given as a question. So in total, we actually found out that 2x plus CB equals to A plus 3. Here we subtracted 2x from this equation and finally found out that the missing side CB equals to A plus 3 minus 2x units in its length. This is the missing side CB, it is equals to A plus 3 minus 2x units in its length. In the next step, we did a construction. That is to say, from point C, we drew perpendicular on AB. Again, from point C, we drew perpendicular on AB. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and AB. This point is point M. By doing this construction, we are doing quadrangle DCMA. In quadrangle DCMA, we have 1, 2, 3 antegons. The sum of 3 antegons is 270 degrees, so 270 degrees plus the size of this four facing again. In total, the mass equals to 360 degrees according to the rule that the sum of the angles in any quadrangle is equal to 360 degrees. And therefore, this four facing angle must be equal to 90 degrees in its side. So, inside quadrangle DCMA, we have 4 angles, and therefore can relate to quadrangle DCMA is a rectangle. But we also know that the opposite sides of the rectangle are equal to each other. So in the big rectangle DCMA, side DC must be equal to the opposite side AM. The opposite side AM. But DC equals to A, therefore the opposite side AM must be also equal to A units in its length. Likewise, according to the same rule, in the same rectangle DCMA, side DA must be equal to the opposite side CM. But DA is 2x, therefore the opposite side CM must be also equal to 2x units in its length. What is the length of this missing side MB? From the drawing, it is very easy to see that MB in total equals to AB minus AM. So MB equals to AB minus AM. So MB equals to AB, that is 3, minus AM, that is A. So in total, MB equals to 3 minus AM in its length. In the next step, I copied the right triangle CMB in a new page and implemented the Pythagoras theorem on this right triangle CMB. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So actually, this is the right triangle CMB that I copied from the original domain. This right triangle CMB, CB squared, that is the square of the hypotenuse, equals to CM squared plus MB squared. CB is A plus 3 minus 2x, therefore CB squared is A plus 3 minus 2x squared, and it equals to CM squared. CM is 2x, therefore CM squared is 2x squared plus MB squared. MB is 3 minus 8, therefore MB squared is 3 minus 8 squared. So in total, we should find out that A plus 3 minus 2x squared equals to that CB squared equals to CM squared plus MB squared, and A plus 3 minus 2x squared equals to 4x squared plus 3 minus a squared. Here we open the brackets on both sides of this equation according to the algebraic identity that A minus B squared equals to A squared minus B squared minus A minus B squared equals to A squared plus B squared minus 2 times A times B. So according to the algebraic identity that I mentioned, A plus 3 minus 2x squared equals to A plus 3 squared plus 2x squared minus 2 times A times 2x. And it is equals to 4x squared plus A minus 3 squared plus 3 minus A squared. 3 minus A squared equals to 3 squared, that is 9, plus A squared minus 2 times 3 times a, this is minus 6a. We open the brackets of this expression, and we found out that a plus 3 squared equals to a squared, plus 3 squared, that is 9, plus 2 times a times 3, that is 6a, plus 4x squared, and we have minus 2 times 2x is minus 4x, so in total this expression equals to minus 4x times a plus 3, and it is equals to 4x squared plus 9 plus a squared minus 6a. We have 9 on both sides of this, we have a squared on both sides of this equation, so a squared will get cancelled. We have 9 on both sides of this equation, so 9 also will get cancelled, and we have 4x squared on both sides of this equation, so 4x squared also will get cancelled. After we cancel those expressions, in this side of the equation we left only with 6a minus 4x times a plus 3, while on the other side of the equation we left only with minus 6a. So total we found out that 6a minus 4x times a plus 3 equals to minus 6a. Here we added 6a and also 4x times a plus 3 simultaneously to this equation, and finally found out that 6a plus 6a is 12a equals to 4x times a plus 3. Here we divided this equation by 4 and finally found out that 12a over 4 is 3a and 4x over 4 is x, so in total this expression equals to x times a plus 3. So in total we found out that 3 equals to x times a plus 3. Here we divided this equation by a plus 3 and finally found out that x equals to 3a over a plus 3. Found out that x equals to 3a over a plus 3. In the next step, we calculated the area of this trapezoid ABCD according to the formula that I presented to you in the beginning of the lecture. Actually, the area of this trapezoid ABCD must be equal to the sum of its two parallel bases, that is to say DC plus AB times the height CM over 2. And again, the area of this trapezoid ABCD must be equal to the sum of its two parallel bases, that is actually DC plus AB times the height CM over 2. DC is A, AB is 3, and CM is 2x. And again, DC is A, AB is 3, and CM is 2x. We have 2 in the numerator and 2 in the denominator, so 2 will get cancelled, and we left only with A plus 3 times x. So in total we found out that the area of trapezoid ABCD equals to A plus 3 times x square units in its size. So here we have it is given us the equation that the area of this trapezoid ABCD equals to 3 square units in its size. So we substituted the area of trapezoid ABCD by 3, and in total we found out that 3 equals to A plus 3 times x. 3 equals to A plus 3 times x, but x equals to 3a over a plus 3, so we can substitute x by 3a over a plus 3. And we get that 3 equals to a plus 3 times x, and x equals to 3a over a plus 3. We have a plus 3 in the numerator and a plus 3 in the denominator, so a plus 3 will get cancelled. We left only with 3 equals to 3a. Here we divided this equation by 3 and found out that a equals to 3 over 3 is 1, so a equals to 1 unit in its length. A equals to 1 unit in its length. And we already found out that x equals to 3a over a plus 3. So now we can substitute a in this equation by 1, because a equals to 1. We did it, and we found out that a equals to 3a. 3a is 3 times 1, that is 3, over a plus 3. A plus 3 is 1 plus 3, that is 4. So in total we found out that the radius of the circle that is described by trapezoid ABCD, x equals to 4 quarters units in its length. X equals to 3 quarters units in its length. Our task is to find out the area of this circle that is described by trapezoid ABCD. Actually, we know that the area of any circle equals to pi times the radius of the circle squared. And therefore, the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle squared is x squared. So in total, the area of our circle must be equal to pi x squared. X is 4 quarters, x is 3 quarters, therefore x squared is 3 quarters squared, that is 3 quarters squared is 3 squared, that is 9, over 4 squared is 16. So in total, we should find out that the area of our circle is equal to either 9 pi over 16 square units in its size, or in terms of numbers, the area of this circle equals to 1.767 square units in its size. Okay, thank you very much.